f of t is equals to sine at. So from Euler's equation, we've seen sine at is the imaginary part, isn't it?
Yeah.
It's the imaginary part, very well. So we are going to have the Laplace transform of sine at. We are going to get it to be a over s squared plus a squared. So we want to see how that is coming about from first principles, isn't it?
Yes.
Are we together? Very good. So from first principles, the Laplace transform of f over t is given by the integral from 0 to infinity of ft exponential negative st dt, isn't it? So where there is f of t, we put our f of t, which is sine at. So that is the integral from 0 to infinity sine at exponential negative st dt. And sine at from the Euler's equation, we've seen it is the imaginary part of exponential jat, isn't it?
Yes.
So the imaginary part we were denoting by that, isn't it? So that is the imaginary part of the integral from 0 to infinity exponential jat exponential negative st dt. Meaning where there is sine at, we now put exponential jat, and this imaginary part is the solution for the sine, isn't it? Are we together?
Yes.
Is that okay? Tuko pamoja? Very good. Now from there, the laws of indices, same base, and remember negative t is to be factorized outside, isn't it? Senor, if you remove negative t, yes, you remain with the negative a. Senor, if you remove negative t, yes, you remain with s. Senor, good. So you are going to have the integral from 0 to infinity exponential. First of all, if you join them, it is jat minus at dt with the laws of indices. Same base with multiplication, you add the powers. That is when you join them, isn't it? But some of these steps you will be omitting because we're just using them for the explanation, isn't it?
Yes.
Are we together? Good. So after that, we have the integral from 0 to infinity. So remove negative t outside. If you remove negative t outside here, you will get negative aj. Or negative ja. Still the same thing, isn't it? Then here you remain with s. So the positive one will start, isn't it? So it is s minus ja, then t is outside, isn't it? Then dt. So if you integrate the exponential function, it remains the way it is, then you divide by the constant of the inner function, isn't it? Because the derivative of the inner function, you can see it's a constant. If you differentiate, you get 1, isn't it? You remain with that constant which is in front of it. Are we together? Very good. So if you integrate that exponential function, just as I was saying, where is the imaginary part? We are dealing with the imaginary part of this integral. It must be there, isn't it? Are we together? The imaginary part of this integral is what gives you the Laplace transform of sine at. Okay?
Yes.
So go on. So we are having what is the imaginary part of, if you integrate exponential, it remains the way it is, exponential negative s minus ja into t. Then you divide by the constant of the inner function. The constant is the whole of this, isn't it? It is negative.
Yes.
Negative into s minus ja, isn't it? Then you put your limits of integration 0 to infinity. So we are looking for the imaginary part of this integral, isn't it? Are we together?
Yes.
Very good. So what do we get? The imaginary part of factorize out the constant. The constant is 1 over negative into that, isn't it? So the constant we have 1 over negative into s minus ja, isn't it? Then you remain with this exponential function. If you put infinity, exponential negative infinity is 0. Then if you put 0 here, everything goes to 0. So exponential 0 is 1. So that is lower upper limit minus lower limit, isn't it? Are we together? So 0 minus 1 is negative 1. See, negative 1 cancels with this negative outside here. So what do you remain with? We are looking for the imaginary part of 1 over s minus ja, because this negative here has gone with the negative there, isn't it? Are we together? Yes. So what do? We rationalize the denominator, isn't it? We multiply with the complex conjugate by changing the sign in the middle, isn't it? So the sign in the middle there is minus, the other side it will be plus, isn't it? You do the same with the numerator to balance s plus ja. So it is like you are multiplying with 1 because that cancels with that, isn't it? Are we together? So we are looking for that, the imaginary part of what? So in the numerator, what do we have? 1 times that will remain s plus ja over, this is a difference of 2 squared, the complex conjugate. It will be x squared plus y squared. So it is just the sign in the middle is positive because of j squared is negative, goes with negative. See there? For a difference of 2 squares. So complex conjugate is x squared plus y squared. So our x is s. So that is s squared. And our y is a, isn't it? And that is a squared. So we are looking for the imaginary part of this. So if you separate them, it is s over this and ja over this, isn't it? That is the common denominator. So we have s over s squared plus a squared, then we have plus, then j into a. So there, a over s squared plus a squared. So if you look at the whole of this problem, you are only interested in the imaginary part of it, isn't it? The imaginary part of it is the part which has the j component, isn't it? So what is the imaginary part? A over s squared plus a squared. And that is the Laplace transform of sine at. Are we together? Very important. Very important. Let us go to the next one. After sine 80, we now want to see the hyperbolic functions, isn't it? Like the cos and the no, we are not interested in those. We are just interested in cos and sage. Okay? Are we together? So that is how we deal with that.